Thank you for attending to this presentation. Today we are going to talk about deltas, a very interesting topic for many sedimentologists, including myself. So we are going into a flow line along this speech. What the objective of this presentation? Firstly, our intention is to introduce the origin and discuss the origin of main concepts associated with deltas and their deposits. Then we are going to discuss new paradigms in deltaic sedimentation. Then we are going to discuss the characteristic of deposits associated with littoral deltas and subacqueous deltas, and to contrast the deposit of a different kind of deltas. And finally, we are going to discuss in some more detail the characteristic of hyperpignal littoral deltas and their deposits, in special with some examples from the Neuquén Basin. According to some definition you can find in the books, Burrell defined a delta as the deposit partially subaerial built by a river into or against a permanent body of water. Eliot, for example, considered the littoral delta a shoreline protuberance formed where rivers enter the ocean. And finally, in this presentation, our definition of delta will be to all those deposits directly accumulated by a subaerial flow in a permanent body of water. For many geologists, the most typical picture of a delta is that of the Mississippi Delta. Bates in 1953 called this kind of delta marine littoral delta. This is the most popular classification ever used by sedimentologists, which is the classification by Galloway. Galloway recognized three different kinds of deltas according to the main diffusion process you have at the littoral areas. The main problem of this classification is that this classification only takes into consideration the subaerial part of the deltas. So we are going to move to some new paradigms about the delta sedimentation. It's very interesting because all our models of delta sedimentations came from the littoral delta, but littoral deltas are very young. All littoral systems we can recognize in nature formed during the last 7,000 years. This is the reason why many littoral deltas appear geomorphologically very big. This is an example of the Macan Delta, in which you can see a very extended delta plane, but the thickness of the related delta deposits is very thin. For example, if you see here, this is 20 kilometers and this is 20 meters. So how we can use these models to try to understand the fossil deposits? Difficult to apply to our reservoir. Now we are going into a more interesting classification, the classification by Bates in 1953. Bates recognized three kinds of deltas: the marine littoral delta, the Gilbert type delta related to a homopignal flow, and very interesting delta recognized this kind of delta he called submarine delta. So it's a density flow generated in the continent. But we had to take care because according to Bates, not all deltas are subaerial. If we compare, for example, the two scales, this is, for example, the Indus Delta, the littoral delta. You can check the size of the littoral delta and the size of the subaqueous delta. As you can see in Bates, it's a contrast between the density of the incoming flow and the density of the water in the reservoir. A key point to understand is that the density of the incoming flow, the density of the flows produced in nature, for example, we have cohesive debris flow, hyperconcentrated flow, concentrated flow, and sediment-laden turbulent flow. These kind of flows are very different in terms of concentration. So we have recently published in the Journal of Paleogeography a new paper with a new classification of deltas. This classification is following the Bates approach. In one side, we have here a logarithmic scale, we have the concentration from sediment-free river, then we have dirty rivers, rivers with the sediment in suspension, and then we go into concentrated and hyperconcentrated flows, and finally cohesive debris flows. On the other side, also in logarithmic scale, we have the salinity of the receiving water basin. So we have freshwater lakes, we have brackish lakes or brackish sea, then we have the marine waters and hypersaline water. So if we contrast the two kind of concentration, the two kind of density between marine or between the water and the flow, we go this blue line. This blue line means where the density is the same. We are going to make some drawing. We can see here the three different fields: the hypopygnal field, the homopygnal field, and the hyperpygnal field. In this field, in the hypopygnal field, the typical situation is that where the river enter with the density is less than the density of the water in the reservoir. So according to this, the river flow is forced to stop and to accumulate delta from deposits here, and you have a buoyant plume here with the fine-grained materials. This buoyant plume contribute to accumulate the prodelta deposits. It's very important that the density difference between the incoming flow, this is fresh water, and the density of the water in the reservoir will affect how the extension of this prodelta will be, because in a hypersaline basin the prodelta will be much more developed because the buoyancy effect of the density contrast will be much more higher. So this is typical situation of the hypopygnal field. So another situation is when you have a bedload dominated river here enter in a basin having fresh water, same density. So density of river is the same that density of water in the reservoir. So all the sediments form this kind of avalanches here, forming typical Gilbert deltas. So as the density contrast, we don't have any density contrast between the density of the river and the density of the water in the reservoir, we are not going to have typical prodelta deposit, fine-grained prodelta deposits. The most common situation here is that of the quartz-grained deltas or Gilbert deltas. This is the homopygnal field. So at the end we have the hyperpygnal field. In the hyperpygnal field, the density of the bulk density of the river is higher than the density of the water in the reservoir. So the flow when reaching the coast is not going to stop here, but is going to plunge, going hyperpignal. So this mixture of fresh water and sediment is going to plunge and is going to travel basinward as a land generated turbidite. Very important, this kind of subaqueous delta. This is the hyperpignal field. But of course we have different kind of sediments or different kind of mixture of water and sediment enter in the basin. So we are not all the hyperpignal flow are not going to be the same. For example, if we have in this field the density in contrast in between the incoming flow and the water in the basin is not strong enough to allow this hyperpignal flow to interact, to erode, for example, the bottom of the basin. So the hyperpignal flow in this situation, typically we have a hyperpignal flow that result from a dirty river with a concentration of sediment in turbulent suspension, and at the same time this concentration is not very strong, so we are going to have a plume here, a hyperpignal plume generated by this hyperpignal flow, but this plume is also maintained by processes, diffusion processes in the marine setting, like for example waves or tides or ocean currents. This is very interesting since this kind of hyperpignal flow is not going to form the typical deposit of hyperpignites we can recognize in the stratigraphic record with channels and lobes, but you are going to have wave reworking or tidal reworking deposits. Very thin bedded deposits in which we have an interaction of an incoming sediment supply from a weak hyperpignal flow and, for example, waves and tides. Which kind of deposit we are going to have in this situation? Typically a prograding, usually geologists call this parasequences, but these in reality are very shallow water delta. Usually this water depth is less than 20 meters. Very interesting kind of deposits, poorly known delta deposit associated to these hyperpignal littoral deltas. So now, according to the importance of this kind of deltas and the fact that these deltas are poorly known, we are going to discuss in more detail these hyperpignal littoral deltas, because these deltas are generated by long-lived weak hyperpignal discharge related to dirty river. The hyperpignal discharge from a weak suspended cloth with fine-grained materials in turbulent suspension that can be aided by coastal diffusion processes like waves and tides. And these deltas, very important, form shallow prograding ramps, shallow prograding parasequence that can extend for tens or hundreds of kilometers with water depths usually less than 20 meters. This is a picture, a cartoon showing the difference between a strong hyperpignal flow in which the density contrast is strong enough to interact with the bottom and to make some erosion in the bottom, and these weak hyperpignal flows in which especially you have these very thin bedded deposits, delta deposits, very commonly to show the deposition associated with wave reworking. We interpret, or we call this short phase deposits. But it's very interesting that in this situation, the hyperpygnal flow is very weak. And some present example in this case is from the Caspian Sea. The Caspian Sea is the largest lake in the world, brackish lake, underfilled lake, and in this situation the Volga River forms at the river mouth this very extended ramp, more than 200 kilometers, with a water depth less than 20 meters. Another beautiful example came from China, the Yellow River. The Yellow River is a dirt river. It goes hyperpygnal nearly continuously. So from the river mouth, you can see here the scale. The water depth of the Bohai Sea is usually less than 18 meters. This is because the hyperpygnal flow is distributed due to the strong tidal action in this situation. So this weak hyperpygnal flow contributes to a very extended distribution of the sediments. Now we are going to see a contrast of the different kind of deltas. For example, we have marine littoral deltas here. Marine littoral deltas are point source. So delta lobes locally has to make this switch, this lobe switch. Then you have the subaqueous delta, subaqueous hyperpygnal deltas, in which you have these shell-fasanton lobes of extravaginal turbidite with channels and lobes. And additionally, we have this new kind of delta, the hyperpygnal littoral delta, will make these very extended ramps with a lot of wave and tidal reworking that contribute to a very wide distribution of suspended sediment coming from these weak hyperpygnal flows. Usually, all these deposits are termed in the geological literature as parasequence, but parasequence means nothing. Usually, geologists relate parasequence with changes in sea level, but also we can recognize this parasequence also in lacustrine setting, associated with this very low gradient ramp, very low gradient deltas, associated with this weak, very weak hyperpygnal flow, hyperpygnal littoral deltas. So now we are going to see some beautiful examples from the Jurassic and the Cretaceous of the Neuquén Basin in Argentina. Here in my back, we have the excellent outcrops of the Neuquén Basin, the Cretaceous in the Agrio Formation, and we are going to see some outcrops. Here we can see these shales with some wavy bedding and lenticular bedding from the Prodelta going into the lower delta front. This is all the progradation that end with this limestone. Probably the salinity of this marine basin was reduced during the accumulation of these deposits according to the volume of fresh water that get into the basin. We can see a 3D model of this outcrop in which we can clearly analyze the different prograding sequences. This is one of the lower one ending with this limestone, and then we have another progradational parasequence going into more sandy succession, and on top we have a limestone. Going to the next step, we can see the upper parasequence or the upper littoral delta. Very interesting. We can see how toward the top the wave reworking increase. We can see some examples in the 3D model. The typical deposit is composed of very thin deposit of this sandstone with wave reworking, Some people call this just shore-face deposits, but it's a typical deposit of delta front in which we have these weak hyperpignal flows aided by waves. Toward the top of the succession, we can see here an increase of bioturbation, some excellent wave ripples, and on top also some starfish, probably suggesting a relative increase in the salinity. Now we are going to another locality in the Neuquén Basin. Going to the center part of the Neuquén Basin, we are going to see some examples now from another unit, the Mulichinko Formation. From this position, we are going to see the characteristic of some hyperpignal littoral deltas in this unit. The characteristic is very similar. You can see these shallowing upward units in which we can recognize a lot of wave reworking, sedimentary structure, and also some hammocky like cross stratification, some hammocky cross stratification. The typical succession from the shales, from the prodelta up to the lower delta from of these hyperpignal littoral deltas. It's very common to find in these deposits hammocky cross stratification. This is an example of the typical hammocky, in this case related to interaction of hyperpignal flows and this wave reworking in very shallow areas, shallow water areas. Going into the northern part of the Neuquén Basin, we can see also very nice examples. One of these, yeah. This is one example of a prograding parasequence, a prograding hyperpignal littoral delta from prodelta to a lower delta front again, and on top, very interesting wave reworking sedimentary structures, also with starfish. Probably suggesting an increase, again, an increase in the salinity, more close to a normal salinity. Okay, we are going to continue now with some conclusion, and for that we are going again into the drawing board. So it's very interesting that the delta represent three different situations according to the efficiency of the delta system. For example, we can have deltas related to very low efficiency flow, very low efficient rivers. In this situation, the river is going to build the typical marine littoral delta with deposits accumulated at the river mouth. This is the most, for many geologists, this is the most common type of deltas, the marine littoral deltas in very shallow littoral areas, shallow water. In addition, if the river discharges a mixture of water and sediment, a weak mixture of water and sediment, the hyperpignal flow can be, for example, be maintained in suspension by waves. In this case, we are going to have this kind of prograding, very low gradient shelf. These progradational systems are much more extended respect to the marine littoral deltas. And this kind of poorly known kind of deltas are the hyperpignal littoral deltas. Hyperpignal littoral deltas has very extended distribution as a sandy shelf, also with a suspended cloud aided by the wave action. And finally, at the highest level of efficiency, the flow can go, or the river can generate a strong, a more heavy hyperpignal flow. This will result in a system of channels and lobes, making the hyperpignal subaqueous delta. The hyperpignal subaqueous delta is the most powerful energy condition of delta system. So, as you can see, the deltas can be very complex. Not only the subaerial littoral delta, or the famous littoral delta in the sense of Galloway, is important. It's very important to understand this kind of deltas we have in the subaqueous part of the lakes or on the sea, because all these deposits are very important to explain the accumulation of our fossil deposits in lacustrine and marine basin. So, very important to understand the different scales between marine littoral deltas, hyperpignal littoral deltas, and hyperpignal subaqueous deltas in this classification. The three respond to different energy conditions. So, marine littoral delta, then we increase the efficiency of the flow. You have hyperpignal littoral delta, and increasing the flow efficiency, you are going to go into a hyperpignal subaqueous delta. In terms of deposits, hyperpignal subaqueous delta typically compose this kind of lobes and channels with deposits that resemble those typical of turbidites or extravaginal turbidites. In this case, marine littoral delta and hyperpignal littoral delta both are fine quartzine upward deposits. But in contrast, marine littoral delta, usually on top you have delta plane deposits with cold and typically delta plane deposits. In contrast, in the hyperpignal littoral delta, column is usually composed of this progradium parasequence. On top we have this limestone representing the flooding surfaces, and this wave reworking with a hammocky cross stratification, usually a lot of wave action, and on top the limestone. This is the main difference between these hyperpignal littoral deltas with, for example, this is marine littoral deltas with prodelta, delta front, and delta plane. Here in the hyperpignal littoral deltas, we have these progradational surface deposits. This is the prodelta, delta front, and here you have the flooding when the river discharge stop. This is related to hyperpignal littoral deltas, typical sequence. And this one, typical succession of hyperpignal subaqueous deltas with channels and lobes, usually forming these fining upward deposits. This is delta front deposit, but related to extrabasinal turbidite. So, as you can see, the stacking pattern of the different kind of deltas is very different, and all depends on the degree of energy discharged by the river. And of course, all this system will be the most powerful because the most transfer capacity of rivers happen during floods. So probably this is one of the reasons that most of the sediment accumulated in our basin are related to this kind of subaqueous deltas. So it was a pleasure for me to have the opportunity to discuss these concepts with you. This is the draft of some of the conclusion we just outlined on the drawing. And once again, it was a pleasure to be with you during this conference. So thank you very much for attending this speech. We are open for questions.